This is the leXsolar SmartGrid Professional, our experimental system of smart grids for technical training. In the case, there are devices required for the experiments such as various energy sources, a consumer, storages, gauges, line resistances, and components for connecting the devices. The smart grid experiments illustrate the working of the classic grid networks, the physical problems due to the integration of renewable energy sources, and the operating principles of intelligent solutions. A typical problem is the risk of overvoltage in a low-voltage strand due to the power supply of private photovoltaic systems in the course of a day. A low-voltage strand consists of many homes and a transformer with a fixed turns ratio, which connects the strand with the medium voltage level. All components are connected parallel to each other to function independently. In the real case, and without private photovoltaic systems, the voltage is at the transformer's highest and falls even further due to line resistance with increasing distance from the transformer. In the end, all households have a different voltage applied. In Germany, the nominal value of the voltage to 230 volts has been defined and may vary for a secure supply to a maximum of only 10% of this value. With the installation of private photovoltaic systems, it may cause overvoltage. We want to simulate this issue in a trial with the smart grid components. For this, we need two base units, the azimuth angle scale, the solar module, with base, and MPP tracker, a power module, measuring devices, 2 smart meters and an AV module, two grid modules, the 2 light bulb modules, the lamp, short circuit plugs, and cables, and a power supply for the power module. Here we have all the required items ready. First, the power supply is plugged into the power module. On the first of the 2 base units, we plug in the voltage source, which, in our experiment, applies a constant voltage on the strand and represents the transformer. This ensures the current supply of the strand. We connect a smart meter to the power module in order to later measure the power delivered to the strand. Furthermore, we connect a grid module and a light bulb with the base unit. They simulate the line resistance between the transformer and the first household, and the first household. For the next section of the low voltage strand, we need the second base unit. It will also be initially equipped with a grid module and a light module. These simulate the line resistance between the 2 houses and the second house. To illustrate the problem of overvoltage, we will install a photovoltaic system with MPP tracker at the second house. Before the house, a power meter is connected in order to investigate when the house absorbs energy from the strand or delivers it. For this purpose, we put the solar module in the base. In our experiment, we connect the solar module to the strand and stick the MPP tracker between the solar module and the house. The MPP tracker ensures optimum power output of the solar module and is also the reason why we set up the second part of the strand from right to left. The module file on the left is labelled in and on the right labelled out. Based on this, it can be seen that the input power of the solar panel must be connected from the left to the MPP tracker. In the experiment, it must therefore be placed at the left end of the base unit. In addition, we insert the smart meter between the house and the power line. In order to regulate the illumination of the solar module, we will use the lamp. This is situated at a distance of 50 centimeters from the solar module with a horizontal beam path. To represent different positions of the sun, we lie the azimuth angle scale under the solar module. It allows us to set the fixed angle of incidence and thereby simulate certain times. To measure the voltage at both households, we use the AV module. Due to the cables, we can connect it at any point in the circuit. Finally, we plug all the short circuit plugs into the base unit. Connect the two base units. And connect the power module to the ground. In this way, the circuit is now closed everywhere. The complex structure is now complete. Now follows the implementation of our experiment. First, we measure the voltage of both households with very low power supply. To this end, we adjust the solar module perpendicular to the lamp and thus simulate a time of 6 o'clock. In addition, we turn the meters on and close when appropriate the switch or select the correct mode. To determine an overvoltage in a household in the experiment, we define for the experiment a nominal voltage of 3 volts, and like in reality, it is only allowed to differ by 10%. In a previous experiment with the same structure without the photovoltaic system, it has already been determined that the voltage values are best observed with a transformer voltage of 3.5 volts at both households. In this respect, we maintain this voltage and turn on the power module. Furthermore, we turn on the lamp and simulate a low illumination of the photovoltaic system. With the MPP tracker, it must be taken to ensure that it performs the mode MPP search. This means that it automatically searches the maximum power. When the LED no longer blinks, the solar module delivers maximum performance. We now connect the AV module to the first household and measure the local voltage. It amounts to 3.12 volts. We then measure the voltage at the second household. Here it is 2.95 volts. These voltages correspond approximately to the state in a conventional low voltage line without a photovoltaic system, since the output is still very low. The transformer feeds a power of 347 milliwatts in the strand. The power at the second household is minus 130 milliwatts. It has an opposite algebraic sign due to the opposite current direction because of the construction. In this case, the sign means that the second household is supplied by the transformer. We now increase the power output by decreasing the irradiation on the solar module. To this end, we reduce the angle of incidence to 45 degrees. This corresponds to the position of the sun at 9 o'clock. After the alignment of the solar module, we firstly detect that the sign of the power at the second household is reversed. This means that the second household is completely supplied and the first household is partially supplied by the photovoltaic system. In contrast, the power of the transformer is decreased. Here, a value of 138 milliwatts can be read. In reality, this means that the adjoining medium voltage grid releases less energy in the strand due to the higher photovoltaic power. We now measure again the voltage of both households. The voltage at the second household now stands at 3.53 volts. The following measurement of the voltage at the first household now amounts to 3.42 volts. When comparing the measured values, we note that both voltages are increased and that the voltage at the second household is now higher than at the first. Therefore, between 6 and 9 o'clock, the voltage and the direction of current flow between the two houses have reversed. Both voltages are now well above the permissible values. With the azimuth angle scale, even more times can be simulated. For example, the specific time can be searched at which the second household is only supplied by the photovoltaic system and the first is powered only by the transformer. In addition to this experiment, still more than 25 experiments concerning the smart grid, photovoltaic, wind power, and storage media can be performed. Another producer standing next to the already mentioned solar module is a model of a wind turbine. It can be equipped with various hubs and blade profiles. With a wind machine, wind power can be regulated on the model wind turbine. When connecting a voltage supply, you have to ensure the correct polarity. The wind power can be regulated by varying high voltages. The second power module can be used as the voltage source. Also, a diode has been added for the use of solar panels and wind turbines in a circuit. It prevents the wind generator from absorbing energy. Furthermore, various storage medias are available as a producer: a capacitor, a lithium iron phosphate battery, and a reversible fuel cell. Their characteristics and that of the solar module can be examined with the use of the potentiometer. In the smart grid experiment, the potentiometer is used as a controllable consumer. In addition to the potentiometer and the light bulbs, there is also a motor available as a consumer. More experimental instructions and interesting background information is included on the accompanying CD. We wish you lots of fun experimenting.